Welcome to the second in our series of videos on antennas. Today's topic is power, range, and licensing. Our main focus is going to be on range. How far can we transmit? And in our little graphic here, we have a transmitter on the left labeled TX and its associated antenna. And then on the far right, we have a receiver. And we're going to use this graphic and a few simple concepts to get a handle on this topic of range. But there are restrictions on the types of antennas and how high you can put them and other things that specifically limit range so we don't interfere with other people. And that's the topic of licensing. Now, in our previous video, we talked about frequency, wavelength, and antenna size. Here on the left, we have a dipole antenna, and we applied a voltage to that, and it created electric fields, E, and magnetic fields shown as H here. And that carried power away from the transmit antenna. For that process of converting the voltages and currents in the transmitter to the electric and magnetic fields that propagate away to work efficiently, the antenna needs to be on the order of half a wavelength. And we're going to use that today. We also talked about some additional antenna types. Non-directional, like the dipole, is reasonably non-directional. It transmits in all the directions except for straight up and straight down here. And there were also directional antennas. A prime example is the one here in the lower left, a dish antenna, which in this case is clearly pointing up towards the sky. This is actually part of the Deep Space Network out in California and other locations throughout the globe. And these antennas can communicate with probes that are around the planets, literally millions of miles away. So how does that magic work? To estimate the range, how far we can transmit, we're going to start with the transmitted power. That's in the voltage and current domain, that's simply voltage times current. Or since this antenna has a resistive input impedance, we can compute power as simply V squared over R. Now, when that power leaves the antenna in the form of electric and magnetic fields, it spreads out generally in all directions. And that's represented in our cover slide graphic with this circle around the antenna. And these partial circles, I simply didn't draw the rest of them. Now, in reality, we can think of those not as circles, but as spheres. So the power is going out away from the antenna in these ever enlarging spheres. And we're going to use that concept today to figure out how much power actually gets over to the receiver. The receive antenna, as you can sort of see here, is somewhat small in comparison with the size of this last sphere, which is huge. And so we only intercept a fraction, a very small fraction in general, of the transmitted power. To figure out what that fraction is, we're going to go through a concept called power density at the receiver, and a related concept of the effective aperture of the receiving antenna itself. Using those two things together, we can then estimate the received power. And with a few other assumptions, we can estimate range. Now, in episode 1, we showed an experiment. We have a transmit antenna in the foreground. It's a dipole. In this case, we are operating at 440 megahertz, and so the length of this dipole was a little over 30 centimeters. In the background, there is another dipole. That's the received dipole. The transmitter and receiver are in this thing called the nano VNA, and the nano VNA instrument shows us how much of the transmitted power from port 1 made it to the antenna connected to port 2. And that's shown in this blue curve. There's a marker at 440 megahertz where the antenna is resonant. Now, the blue curve has a readout, and in the upper right it says minus 11.98 dB, which is basically minus 12 dB. What does that mean? Well, if you're familiar with dB, you may know that minus 10 dB would mean that we've received a tenth of the power that was transmitted, but this is minus 12. And if we punch our calculator, we can figure out it's actually about a 16th of the power that was transmitted. So where did the other 15/16ths of the power go? Where did the most of the power go? Well, it went out to other directions other than the direction where the receiver is. Now, in this particular experiment, the antennas are fairly close together, say 25 centimeters, which is a quarter of a meter or somewhat less than a foot. But if we increase the distance between the transmitter and the receiver, we would expect to get less power. And in fact, we do. Here, we've doubled the distance to about 50 centimeters, about half a meter. And if we look at the readout on the right, the blue curve shows we have about minus 18 dB now. That's 6 dB less than before, which translates to 1/4 of the amount of power we were receiving before. So this is very important to remember, and we'll see why shortly. But remember that every time you double the distance, you lose about 6 dB in your received signal strength. One important caveat to that is that that's the case if the signals are in what's called free space, so that this transmit signal goes out in all directions, as we said, and it doesn't hit anything or get blocked by anything, etc. Those complicating factors we'll look at very briefly at the end of this, but we'll also go into in later episodes. But let's take the simplified case first, because that's how we learn stuff. So here are some actual computations. Let's assume that the transmitter puts a RF voltage on the antenna of V sub t, T for transmit. And let's assume that the transmit antenna is like a dipole. So it is what's called resonant, which translates into it having a resistive input impedance. And we call that R sub ANT, R sub antenna. Now, for a dipole, an ideal dipole, our antenna is 73 ohms. But in practice, a lot of times antennas are engineered to be 50 ohms. And in fact, some dipoles, if you don't put a balun on them, are closer to 50. So I'm using 50 in this example. And I'm using 1 volt because it's a nice round number. So 1 volt RMS into 50 ohms, how much power is that? That's 0.02 watts. P sub t, the transmitted power, is 0.02 watts or 20 milliwatts. That's how much power is leaving the antenna. Next, we want to figure out how much power actually gets into the receiver. And we're going to do that in a couple of steps. First, we're going to talk about the power density at the receiver. And that is a distance d away from the transmitter. And to keep things simple, assume that all the power that's radiated from the transmit antenna goes out in a sphere. And that sphere enlarges as it travels away from the transmit antenna. So over at the receiver, the radius of the sphere is d. What's the surface area of the sphere? Well, the surface area of the sphere is 4 pi r squared, but here it's called d. And so the transmitted power, the 20 milliwatts, is now spread over a surface area of 4 pi d squared. So what's this GT thing? That's the transmit antenna directivity gain. And that's going to play a very important role when we talk about directional antennas. But let's talk about what it means here. Remember that our dipole antenna transmits well in this direction, which is called broadside to it. It does not transmit well off in this direction or this direction called end fire. But all the power, all 20 milliwatts, is leaving the antenna. If the antenna transmitted equally well in all directions, then the formula that we've talked about so far would give us the right result. However, since some of the power does not go out in this direction or that direction, more power is going out in the broadside direction than a so-called isotropic antenna would do. So it's a little fudge factor. Basically, GT here is a factor of 1.6 for a dipole. So it's not that important for what we're talking about. So the transmitted power spread over the surface area of the sphere is a density in the sense that it's now watts per square meter. How do we get back to what we want, which is the watts coming into the receiver? Well, we have watts per square meter, so we need to multiply by an area, and that's shown in the lower right here as area effective. It is essentially the effective size of the receiving antenna. So let's take a look at that receiving antenna. It has this length, but what's the area? Well, we might be tempted to think it's this length times the width of the rod here, but it's actually much bigger than that. It's actually about the square of this length. And that's where the effective comes in. the effective area of this is larger than the physical area of these rods. So let's put this all together and get an answer. We transmitted 20 milliwatts, 0.02 watts. That power spread out roughly in a sphere. We compensated for the fact it wasn't exactly a sphere by a GT, the gain of the transmit antenna, which gave us a power density in watts per square meter. So we simply multiply the power density times the area, and that'll get us watts. That'll get us the received power. All right, so let's get an answer. The example, GT is 1.6 because we're using a dipole. The distance, we said, is half a meter in this experiment. And so we use the formula and we compute the power density as 10 milliwatts per square meter. Then, using the effective area of the receive antenna as roughly the square of its length, there is a fudge factor. It's about 0.5. You can get an exact value if you Google for effective area of dipole, but I'm not worried about that. What we're trying to do here is just understand how this works. So this 0.5 is perfectly fine for our calculations. Our receive antenna is a half wavelength dipole at 440 megahertz. So that works out to about 68 centimeter wavelength or 34 centimeter, 0.34 meter length for the dipole. Area effective works out to be 0.058 square meters. We multiply that by 10 milliwatts per square meter and we get about 0.6 milliwatts. Now that's for this particular distance. If we didn't change the transmit power and we didn't change the antennas, but we actually double the distance, what would this number become? Well, remember, every time we double the distance, we get about a quarter of the received power. And so this would drop to about 0.15 milliwatts. And 0.15 milliwatts is 6 dB less than 0.6 milliwatts. So is 0.6 milliwatts or 0.15 milliwatts a lot? Well, actually for receivers it is. At these kind of power levels, you could actually build, in theory, something like a crystal radio using a Schottky diode. And this would be enough power to drive a headphone, for example, and listen to AM signals. But if you increase D much more, these powers drop very rapidly. And pretty soon you need some amplification in the receiver. And if you amplify enough, you could receive very, very weak signals. So let's take a look at that and the question of how far can we actually transmit. And I'm going to take a somewhat different approach to figuring out the maximum range than you might see in a textbook. This approach is going to leverage what we've just talked about and also bring in some other factors like the maximum gain that you could actually have in a receiver. In our Radio Design 101 series, where we designed and built an FM broadcast receiver, we found out that the gain that we were designing for was limited to about 100 dB. We didn't need more than that. And that was for two reasons. One is that in addition to the signal coming into your receive antenna, there's actually thermal background noise. And there's a formula for that shown here, KTB, where K is Boltzmann's constant, T is temperature in degrees Kelvin, and B is bandwidth. I'm not going to go into the details on that today, but suffice it to say that that limits us to received gains on the order of 100 to 120 dB. Other things also limit us, like interferers, other strong signals that might be competing with a very weak signal we're trying to receive. And we saw that in the epilogues to the Radio Design 101 series. So let's go back to the previous slide and see if we can use that 100 dB, we'll just use a nice round number, to calculate the distance that we could get with our 20 milliwatts transmitted and some dipole antennas. Remember, every time we double the distance between the transmitter and the receiver, the signal falls by 6 dB. This is actually called 1 S unit. If you're a ham radio person, you may have seen a meter like this, which has a scale with S units, and then dB over S9 is what it's called. But no matter, let's just remember 6 dB per doubling of distance. So at the distance in our experiment, which was 0.5 meters, we had enough received power. We didn't really need any amplification. But if we double that distance, we're going to need some. And if we double it again, we'll need more. And if we double it again, we'll need more. And every time we double the distance, we need 6 dB more gain. So if we have 100 dB of gain in our receiver, how many times could we double the distance? Well, we take 100 and divide by 6. We get 16.7. So we could double the 0.5 meter distance more than 16 times if we use the maximum gain. It's going to work it for 16. So how big would our distance become? We started with 0.5 meters and we double it. And then we double it again and we double it again. So we have 2 times 2 times 2. And we can do that 16 times, which is 2 raised to the 16th power. Maybe a little more, but we're just going to do a quick calculation here. And in the title of the slide, I call this a rough back-of-the-envelope estimate of potential range. This is what you might do in a coffee shop if you forgot your calculator and you left your cell phone in the car and you're just trying to rough something out. You use a few things you know. For example, 100 dB max gain, 6 dB per doubling of distance. And we can calculate that's 16. 2 to the 16th, what's that? Well, if you're a computer person, you know that's 65,000, 384 or something. I just remember it's about 65,000. So I now have 65,000 times 0.5 meters, and that works out to be 32,000 meters or 32 kilometers. And for us who work in miles, that translates to 20 miles. 0.62 times whatever it is in kilometers. So in theory, with this setup, with these two antennas, we could put the receive antenna 20 miles away and receive the signal. And that might actually be the case if you're, for example, flying over in an airplane at 5 or 6 or 7 miles altitude, you could receive this signal. Which is why when we're doing experiments like this, we run them at very low power, much less than the 20 milliwatts we used in the example, and we generally want to be in a shielded environment so we don't interfere with others. Which brings us to our final primary topic today, which is licensing. Licensing is a very big topic itself, but it can be summarized in the 3 bullets shown here. From the very earliest days of radio, more than 100 years ago, it became apparent that different users would interfere with each other. And so government bodies got involved and designated certain frequencies that were allowed to be used by different groups. But they don't only designate frequencies. They also designate maximum power levels that can be used and restrictions on the antennas. And I found that out when I was a teenager. I got one of these radios. It transmits 100 milliwatts on specific frequencies in the citizens band, but the antenna was limited to be 60 inches legally. And as we'll see, for what's called terrestrial communications, where radio signals bounce off buildings and trees and ground and other things, that really limited the range to under a mile. So I wanted to transmit farther, and therefore I had to get licensed. The best path for individuals is arguably an amateur radio license, or whatever it's called in your country. All countries have these sorts of things. In the United States, there is a group called the American Radio Relay League. Here is the URL for that. You can just search for ARRL or go to this link and find information on getting licensed. And once you do get licensed, you have a host of frequencies that you can operate on legally. And with these sorts of things, you can transmit pretty much around the globe on the best of occasions. So here's a quick example of that. I restored this radio, and once I did, I put it back on the air, and here's some of what I received from Kansas. So the signals you're hearing are from hundreds of miles away.
Big signal, Sequoia 5 and 9 plus 10 dB. Weather here is cold, -5 C with scattered clouds, but no snow, no snow. And I live in northern Minnesota, very close to Canada.
Okay, so in summary, here's what we've learned today. It's easy to compute the transmitted power if you know the voltage and the antenna resistance. Then, assuming your receiver is at a distance d from the transmitter, we can calculate the power density using this equation. And finally, get the received power if we know the effective area of the receive antenna. And we looked at some specific examples of that. There are some caveats. These expressions only apply in what's called the far field. But that's generally okay because the far field begins at a couple of wavelengths away from the antenna. However, a very important caveat is that this formula for the power density is only true for free space, not if you've got things in the environment. And those things could include obstructions, things in your way, but also just the ground itself. Signals can bounce off the ground and interfere with the main path signal. And what happens when you analyze that is you find out that the d squared term can become something like d to the fourth or even worse. Unless one or both antennas are well above ground or very directional and there's nothing in between them. We have a line of sight. If that's not the case, then we have d to the fourth down here, and our 32 kilometers or 20 miles will shrink to like 130 meters or 420 feet, which is not necessarily a bad thing. If you've got, for example, Wi-Fi inside a building like this, you do not necessarily want that Wi-Fi getting out because it could interfere with Wi-Fi on the same channels being used in other buildings or outside. So modern industry actually takes advantage of this sort of self-limiting range, which occurs when you're in an environment like a house or a building or just out on the earth somewhere. That said, these expressions do work for things like line of sight from a dish antenna to something in a space probe on another planet. And so things like 20 miles aren't much compared to 100 million miles for the path from the Earth to Mars. So how do we reach such long distances? Well, we could increase the gain, GT, and we'll see in later episodes how we can do that with large aperture antennas. We can also increase the effective area of the receiver antenna, again using a large aperture like this dish. And that can allow us to double our distance another 10 or 15 times, especially if we increase the transmitted power at the same time. But before you can use a lot of transmit power or basically radiate at all, you need to get licensed, or make sure the equipment you're using works on an unlicensed band and follows all the restrictions on power and antennas. Okay, that's it for today's episode. Thank you for watching. I hope it's been enjoyable and educational. We took some fairly simplified techniques here. In future episodes, we'll go into more detail and cover range calculations using more traditional methods like the so-called Friis equation, and look at the transmit gain of aperture antennas like this dish, and also look at some real-world measurements of range in this building or from this building out into the parking lot. Hope to see you there. Bye.